Hi, welcome to the third Math Basics video. Third Math Basic video. This one's going to be all about surds. So that basically means anything that's under a square root sign that you can't do that you can't get a whole number result for the square root. So they're a type of irrational number. So here's an example: the square root of 5 is a surd because you can't simplify it, whereas the square root of 4 just equals 2, so it is not a surd. Surds are irrational numbers. There are also some other irrational numbers like pi or Euler's number, which is e. These have decimal numbers that just go on forever, but they don't repeat. So this is different to, say, a third, where a third is 0.333 and so on, with more and more threes. But this is just a repeating pattern, so because it's repeating, that is not irrational. Okay, so we're talking about surds, square roots of things, and we're going to cover these 5 different sort of topics within it: multiplying surds and dividing surds, and within that, what we're really talking about is simplifying surds. We're also going to learn to add and subtract surds, and you're going to learn that this is going to be the same as algebra. I'll show you that in a moment, actually. Same as algebra. Then you're going to be rationalizing the denominator. In other words, making the denominator a rational number instead of an irrational number. So getting rid of the surd from the denominator. And then lastly, we're going to think about using conjugates, and I'll explain that when we get there. Okay, so first thing is multiplying and dividing surds. So multiplying surds. If we have a surd and we multiply it by another surd, we can just do the multiplication first and then put the square root sign over it. So, and there's a very similar rule for dividing as well, which is if you take a surd and divide by another surd, you can do the division first and surd second. A over b, square root over all of it. Okay, so these two things, they help us simplify surds. Let's take a bit of a look at a couple of examples. Alright, so let's look at some examples. We've got, let's do a very, very simple example. Let's have the square root of 2 times the square root of 5. I'll just do the 2 times 5 first, and then do the square root, which gives us the square root of 10. Or here's another example. Square root of 10 divided by the square root of 2. I'll do the division first. 10 divided by 2 is 5, so the answer is the square root of 5. Now obviously these two examples, they're sort of like going backwards compared to the other one. So there's an extremely simple idea. Now this helps us simplify surds in the following way. So suppose our example was simplify the square root of 28. What we need to do is look in 28 if there's a square number. So we know that 28 is 7 times 4. So we can write 4 times 7 instead of 28. And then we can sort of go backward and say, well, that's going to be the square root of 4 times the square root of 7. And the square root of 4 is 2, so that's 2 times the square root of 7. So square root of 28 equals 2 square root 7. Okay, let's try another example. Let's say simplify the square root of 8. Well, we look for a square number in there. So obviously our square numbers are 2 times 2 is 4, 3 times 3 is 9, 4 4 is 16, then 25, then 36, and so on. So in 8, I can take out a factor of 4, so that's going to be square root of 4 times 2, which is going to be the square root of 4 times the square root of 2. Square root of 4 is 2, so it's 2 root 2. So square root of 8 is 2 root 2. There we go. Okay, let's do another example that's looking a little bit more complicated. So we might have 3 root 6 times 5 root 3. Okay, so to simplify this one, it's going to be, well, everything is multiplied by everything else. So this is just 3 times, I'll just write it out in longhand, so this is missing a few times signs here, so 3 times 6 times 5 times root 3, and it doesn't matter which order you do your multiplications in. So we're going to do the 3 times the 5 first, giving us 15, and then our surds multiplied together, 6 times 3, 18. Now we look to see if you can divide 18 by any of these, and I think, oh yes, 9 is one. Let's get some more space. So I can have 15. 18 is actually 2 times the square root of 2 times 9. So that's 15 root 9 times root 3. Oh, sorry, root 2, of course, from this 2 here. Root 9 is 3, so that's 15 times 3 root 2. 15 times 3 is 45 root 2. There we go. So when we multiplied our original question, whoops, that was a bad line. This one here, even though we had a root 6 and a root 3 here, in our answer we have a root 2 going on. Okay, so you can see that that is that's quite a lot more simple looking. So there we go. That is that's sort of simplifying using multiplying and dividing. Now, next thing, number 3. Next thing is adding and subtracting surds. Adding and subtracting. Now, when you add and subtract surds, it's a lot like you were doing the same thing to algebra. And we all know that to add and subtract algebra, you need to have like terms. So it's like algebra, you need like terms. So let's do an example. If we have like x plus 3x plus 2y minus 1y plus xy. Okay, so we see that like terms are the x terms here are like terms with each other. So we can add those, giving us 4 x's. The y terms are like terms. So we can do 2y's minus 1y, that's plus 1y. And this xy term is its own term, so we've got to leave that. So in algebra, to add or subtract, you need like terms. So in surds, we need like surds. You need like surds to add or subtract. So if we had something like 3 root 2 plus 7 root 2, we notice that we've got the same, that's a 2. We've got the same surd in it, so we can add it up because they're like surds. 3 plus 7 gives 10 root 2. There we go, 10, that's a 10. Alright, so let's do a more complicated example. I might have 7 root 3 plus 6 root 11 minus 8 root 3 minus 10 root 11. Okay, so here we do the different like surds with each other. So we've got a root 3 term here and another root 3 over here. So 7 minus 8 gives us minus 1, so that's minus a root 3, plus, and then these two terms are like surds as they both contain root 11. So 6 minus 10 gives minus 4 root 11. And that's our final answer. Okay, let's do one example now where we're combining our knowledge from adding and subtraction with our knowledge of multiplying. So let's have a question where it says expand the following 2 root 2 plus 1 multiplied with root 6 minus 4 root 3. Okay, so we know the way we need to do this is to multiply everything in this bracket by everything in this set of brackets. So we're going to do 2 root 2 times root 6, and 2 times 2 times root 2 by minus 4 root 3, and then 1 by root 6, and 1 by 4 root 3. So 2 root 2 times root 6 is going to be 2 root 2 times 6. 2 root 2 times minus 4 root 3 is going to be negative 8 root 6. So I'm multiplying the number out the front first, and then the square roots are sort of multiplying together as well. Now the 1 times root 6 is root 6, and 1 times minus 4 root 3 is minus 4 root 3. So now I better complete this bit here. So let's see, we've got 2 root 12 for that bit there. Now I've got a root 6 term and another root 6 term, so they're like surds. So that's going to be minus 7 root 6 there, and minus 4 root 3. Now I noticed that root 12 is not in the most simple form that it could be, because I know that root 12 could be written as root 4 times 3, which is root 4 times root 3, which is 2 times root 3. So I'm going to change the root 12 to 2 root 3. So the 2 gets multiplied by that 2, giving 4 root 3. Okay, now I've got some more like terms. I've got a 4 root 3 and a minus 4 root 3. So because they're exactly the same, they're going to cancel each other out, leaving us with a minus 7 root 6. So there you go. That is our total answer to multiplying these two surd expressions together. Back to the top. Here we go. Alright, we're up to our fourth part, which is rationalizing the denominator. Okay, so rationalizing the denominator basically means if we have got something like this, 1 on root 3, we don't want the surd to be at the denominator. It's just sort of something to do with elegance, I suppose. Looks better. So the way we do rationalize the denominator is we remember from our fractions, we can find equivalent fractions. So we need to find an equivalent fraction to this that doesn't have the square root at the bottom. Now when we're doing equivalent fractions, we remember that what we're allowed to do is multiply it by 1. But we're going to write our 1 in a more clever way. So we've got 1 on root 3. And instead of writing 1 like that, I'm going to write a 1 as root 3 on root 3. Because look what happens. The top I've got 1 times root 3, that's root 3. And at the bottom I've got root 3 times root 3, which is 3. So now my denominator has been rationalized. 3 is a rational number, so the denominator has a rational number, which is what we're looking for. So that is done. So we found that 1 on root 3 is root 3 on 3. So the key here is we choose a 1 that will give us a rational denominator. So if the denominator is just the square root of something, we multiply it by that sort of term there. So let's do some more examples, which will make this a little bit more clear. So suppose we have 1 on root 2. Well, what we do, we multiply it by 1, but we're writing 1 as root 2 on root 2. So at the top we get root 2, and the bottom, root 2 times root 2 is 2. And let's just do one more example. Let's say we have 3 over the square root of 5. Well, we're going to multiply that by 1, written as square root of 5 over the square root of 5, which is going to become 3 root 5 over 5. Okay, let's do one more example. Let's suppose we have 3 root 5 over root 6. Going to multiply that by root 6 on root 6, giving us 3. Now, root 5 times root 6 is root 30 over root 6 times root 6 is 6. Now, let's see. Okay, so now our 3 and our 6, we can make that slightly more simple because 6 is, of course, 3 times 3. So that's 3 root, that is root 30 over 2. And that's as simple as it can get. Okie dokie. So there we go, rationalizing the denominator, and I think you can see the pattern going on fairly clearly there. Okay, last part is part 5, using conjugates. Using conjugates. Well, first you need to know what the heck is a conjugate. Basically, if you have a number like 5 plus the square root of 2, its conjugate is 5 minus root 2. Okay, so you can see that it's basically the same but with a different sign going on. Or here's another one, if you have square root of 7 minus the square root of 5, its conjugate is root 7 plus the square root of 5. Okay, so the sign of the first term is the same, but the sign of the second term is different. Okay, so that's what a conjugate is. And it's most common to have this first type that we had. So have one where the first number is rational, so it could be 2 plus, and then the second number is irrational. So the conjugate of 2 plus root 10 is going to be 2 minus root 10. So that's what we refer to as the conjugate. Okay, so no doubt you're wondering why a conjugate might be useful. And the answer is that it's all just about rationalizing the denominator, but when the denominator is a little bit more complex. So take a look at this example. Take a look at 3 divided by 3 minus root 2. Okay, so we can't do multiplying by root 2 on root 2. Let's just try this. You're probably thinking, well, let's just do root 2 on root 2. And what will happen is you get 3 root 2, and then on the bottom you get 3 root 2 minus 2. So there's still this irrational part on the denominator, so that didn't really work. Okay, that's a cross for wrong, by the way, not at times. So we need to try something different for that example. So let's get rid of, let's just write it again. So we're trying something different for that example, 3 on 3 minus root 2. What we're going to do is multiply by the conjugate on the conjugate. So the conjugate is 3 plus root 2, and we need to multiply by 1, so we need to multiply by 3 plus root 2 on 3 plus root 2. Now take a look at what happens. We get 3 times 3 is 9, 3 times root 2 is 3 root 2. And on the denominator we get 3 times 3 is 9, 3 times root 2 is 3 root 2, minus root 2 times 3 is minus 3 root 2, minus root 2 times root 2 is minus 2. Now do you notice that this term, these two terms with surds in the denominator, are going to cancel each other out. So we're going to have 9 plus 3 root 2 divided by, now those have been cancelled out, so we've got 9 minus 2, 7 on the bottom. So now our denominator is rational, so we have rationalized the denominator. So the key bit was we looked at the conjugate of what's on the bottom, looked at the conjugate, and we multiplied by the conjugate divided by the conjugate. So let's do another example to get used to it. So we're going to rationalize the denominator of root 2 on root 11 plus 3. Okay, now here I'm trying to be a little bit tricky because I've swapped the order of the root 11 and the 3. So the conjugate of this is actually 3 minus root 11. Okay, so what we're going to get is root 2, 3 times root 2, minus root 2 times 11 is 22, divided by root 11 times 3 is 3 root 11, root 11 times minus root 11 is minus 11, 3 times 3 plus 9, 3 times minus 11, minus 3 root 11. So these two terms will cancel out, and we'll get 3 root 2 minus root 22 over negative 2. Now, similar to having the denominator rational, we also want the denominator to be positive. So to make this positive, we're going to multiply the whole thing by minus 1. In other words, we're making everything change sign. So we'll get minus 3 root 2 plus root 22 over 2. So now the base is positive. So everything, the sign has swapped for everything. Okay, let me do one more example of that type because it's a little bit tricky. So let's have root 3 on 10 plus root 2. Got to simplify this. Well, multiply by the conjugate over the conjugate. 10 minus root 2 over 10 minus root 2. Okay, so we get 3 times 10 root 3 from those two. Root 3 times negative root 2, negative root 6 over. Now, if you've looked at the patterns, we're going to get 10 times 10, we're going to get 100. A few things will cancel out and we'll get minus 2. So you can try that yourself by doing the extra steps that I've skipped. So we get 10 root 2 minus root 6 over 98. And there we go, we have finished. Rationalizer has been denominated. The denominator has been rationalized. Okay, there we go. There's everything you need to know about surds, and probably a little bit more. So a lot of this rationalizing the denominator stuff, it's kind of more about elegance than it is about usefulness sometimes. But you definitely need to know it for maths methods. Okay, that's all. See you in class.